Okay, I propose that we start. Is that okay?
Yeah.
So, welcome to this fourth Artificial Intelligence Colloquium of the RWTH AI Center. So today we have another great speaker. This is the fourth colloquium that we have. Today's speaker is Andreas Schuppert. I will introduce him in a minute, and he will be talking about the relationship between AI and healthcare. So Andreas is leading one of the around 80 groups that are involved in our AI center. So in a few seconds, I will tell something about the talk and Andreas, but about the organization. So we will have a talk of about 45 minutes, followed by a Q&A session of 15 minutes. I think everybody knows how Zoom works. There is a Q&A feature that you can use. So you can already start thinking about questions while Andreas is talking. So I think after 2 years of Corona, we were just talking about that in the chat before, is that I think everybody sees how important it is to have accurate data to make predictions related to healthcare processes. And Andreas is one of the developers of the DIVI predictive simulation models that predicts the load of ICUs. And because of this, he was frequently in the news over the last, let's say, year or 2 years. But this is just one of the many things that Andreas is working on. So Andreas Schuppert is a professor of computational biomedicine and the founding director of the Joint Research Center for Computational Biomedicine at RWTH. And in that role, he has also been working with Bayer as a key expert in the field of data analysis and modeling. So if you look at his research, the focus is on hybrid modeling technologies, typically using a wide range of mathematical models, ranging from simulation, time series, scale-free networks, neural networks, and many more things. And the applications of his work are typically in healthcare, ranging from intensive care, oncology, electronic medical records, etc., etc. So the title of his talk that everybody has seen is very intriguing. It's Artificial Intelligence, Key to Next Generation Healthcare. And he will focus on the challenges of predictive models, specifically if you do not know exactly how the mechanisms behind them work. And he will illustrate that using his COVID-related research. So I'm excited to listen to his talk, and let's give Andreas a warm welcome. The floor is yours, Andreas.
Okay. Yeah, thank you, Will, for the kind introduction. So welcome to this afternoon seminar. So Will, in my title, you forgot the question mark, and I primarily want to focus today on the question mark. So I would like to start first of all to introduce a little bit why AI in medicine is indeed associated with a huge hope from a medical point of view, and which created a hype, but there are some scientific elephants in the room, and in the following parts of my presentation I would like to address 2 of these elephants and how we can get rid of it. Okay, let's first start about artificial intelligence, which is supposed to be the next revolution in medicine. So starting from the Spiegel and Handelsblatt and other normal newspapers up to high impact scientific journals like Nature and Nature Medicine, all of them address artificial intelligence to be the hope for the next revolution in medicine, which may turn medicine to turn, let's say, from the medical art to medical science. Okay, and so even there have been claims that artificial intelligence can even save our healthcare systems from going bankrupt, and so this is indeed, you see, there is a lots of hype, lots of hope in it. And indeed, if we look a little bit more in detail, where in medicine this hope arises from and where are the medical unmet needs, then we see for artificial intelligence applications and solutions, then we find primarily this hope based on the increasing complexity of healthcare in aging societies we are faced with. So there are I would like just to address three key topics which are of high relevance today. First of all, there is the area of rare diseases. These are typical diseases which arise only in a very few patients, but are associated with quite rare aberrations, very often in the genome or in the proteome or in other omics, molecular levels. And here the key is to identify these patients in huge sets of data. So there are maybe only 10, 20, 100 patients in Germany, throughout Germany. And it's far from being trivial to diagnose these poor people precisely. So they run for years from one doctor to another one, and no doctor can give them a precise diagnosis. And that is indeed why one hopes that based on the huge data sets which are now available, artificial intelligence may help to give the doctors, let's say, a ground truth patterns characterizing the ground truth of, let's say, healthy people in order to identify them much more precisely and much quicker the people who are affected by a rare disease. So that's roughly the hope of on artificial intelligence in rare diseases. In oncology, there is a lot of hope as well. Oncology is primarily driven by aberrations on the genomic level. These aberrations can be very simple aberrations driven by one gene only or by multiple genes, but essentially each tumor has its individuality. And and because of this individuality, therapeutic strategies mostly are effective only in surprisingly low percentage of the overall patients, or maybe 20%. And this is especially true for modern therapies, not the old ones, but for the modern therapies, which have less side effects than the old ones. They are much less effective, or in some patients they are very effective, others they are not. And unfortunately today it is very hard to predict in which patient the therapy will be effective and how to design an effective therapeutic scheme in an individual patient. And there the hope is that AI may help here. Another area where we are intensively working in is intensive care. So in intensive care, there may arise very often lethal syndromes like a sepsis or a multi-organ failure, kidney failure, lung failure, etc. And very suddenly, and one could really save lives by early prediction from the data, from the monitoring data, longitudinal monitoring data, which are assessed routinely in ICU stations, and to learn from them what will happen and to design optimized interventions based on these data. This is the hope for artificial intelligence in intensive care. But not only in clinics, in public health as well, AI may play a key role. I hope that we will be, with the help of AI, we may be better prepared for the COVID waves, which are expected to come up next winter time. So that's my hope, of course. I'm not sure whether it will happen, but we have to work on it. And so we have to learn individualized, optimized strategies on the one side for keeping healthy. And the other side, in public health, we should learn to manage epidemic and pandemic scenarios. So you see, from a medical point of view, there are indeed lots of huge unmet medical needs which can be tackled by AI, and where AI can play a key role to help to improve our medical care. So what is the status today? What can we do today? So primarily, most prominent applications of AI in medicine are based on the one side, on image analysis. So here you see one example is a very famous study published by the Google Alpha group. And what they did is they analyzed about more than 100,000 patients with ophthalmologic disease, so with retinal fundus photographs, and focus was to detect earlier diabetic retinopathy, and they trained with these background images. They trained a convolutional neural network, and they were able to diagnose early such retinopathy, diabetic retinopathy, and with a very good precision. You see here the receiver operator curve, and Google asked doctors, so ophthalmology specialists, to do themselves such a diagnosis on the same data. And you see that the AI really showed the same precision as the specialist. So that is what AI in such image-based diagnostics can even do today. And what was a clue of that paper is that this receiver operator curve of the AI allowed to identify the special individual preferences of individual doctors. So apparently some doctors are a little bit more careful, other doctors are less careful, they are more aggressive. And so one can use even these AIs as a side effect to characterize doctoral practice. And so apparently this may have an impact on public health as well. There are lots of others of image-driven applications which are going to be applied today. So, for example, in tumor diagnostics, image analysis plays a key role as well. So here you see one example which was performed in Aachen Hospital, where it was where a group around Jakob Kart and Tom Lüde were able to predict microsatellite instability, so genomic characterizations of a tumor just by analyzing photographs. So that was a really surprising finding, that image analysis of photographs can substitute genomic diagnosis. So, and this is indeed from a practical point of view of healthcare, this may have a great impact. And currently we have, there is another Nature Medicine paper which has been accepted last week in the same field. So that is an area which can really have an impact. Wound healing is an area, especially in the context of diabetes, plays a key role, where it has been shown that AI-based diagnostics can help as well. Retina diagnostics, optometry is an area, and all in the full range of radiology activities from MRT, PET, and sonography. All of them are affected by artificial intelligence-based image analytics, and there are tons of papers describing studies where it really worked. Another area where AI may play a key role in medicine is a time series analysis, is patient monitoring using time series analysis. And that's primarily driven by the success of wearables, so wearable monitoring systems. And here it really may be a game changer in the way we do healthcare. So, for example, because simply we can monitor using these systems, we can monitor chronically ill patients, and we can leave them at home, and we can identify by the monitoring systems very early when they are at risk to suffer from a severe syndrome, and then the doctor can be alarmed. So the system can set an alarm, and so the patients can be then admitted to hospital and get an optimal care. So that is indeed in cardiology, that is indeed a great issue, and it has the potential to change the way we take care of chronically ill patients. So there are in urology, and there are very promising and interesting studies reported that, for example, early diagnostics of neurological disorders, which are really hard to diagnose with the standard state of the art. So, and AI-based analysis showed that it might be possible, let's say, to identify early neurological disorders like depression or dementia by simply a face image classification. So They have us. So you see, there are lots of papers and studies which have been published, but, and that is what I want to tell you, it is not easy. So there have been, the most prominent example that such approaches can fail, even if hundreds of millions are invested, is the IBM Watson system. So IBM, with the Watson system, tried to move into this healthcare area with really huge investments in oncology and and it served for other hospitals. And they almost fully failed. In almost all trials, they could not add real value to the state of the art, which is currently run in these hospitals. And I have learned a couple of weeks ago that now IBM is going to sell all these healthcare business with the Watson system, and that is definitely what should tell us, okay, there must be some elephants in the room which have to be thrown out before we can realize the full potential of AI. So what are these elephants in the room? Some of these elephants, there are maybe more of it, but I think the most prominent elephants one of them is that we should be aware that currently, this AI hype is mainly driven by deep learning technologies. And there are now more and more publications coming up showing that and comparing deep learning and alternative learning systems like random forests, etc., on real-world clinical data, which are not just image recognition or time series analysis problems, and they showed that surprisingly, deep learning showed no superiority on observational data with a more complex data structure than just imaging or time series monitoring analysis and in medicine. So that was just an observation without any explanation why it is. And so maybe we are going to use and to develop simply the wrong methods for a generic set or more generic set of problems. Another point which has to be tackled is that at least supervised and even more unsupervised learning needs very large data sets. So Google Alpha for these retinopathia study used 120,000 images of retinopathy and they asked for each image 10 doctors to characterize that, to annotate that. And this is a tremendous effort to be invested in simply in annotation of this data before you can start any training of an AI. And Alpha, I've heard that even Google Alpha admitted, confessed that this effort is too high to repeat. So even Google Alpha is not able to repeat such a tremendous approach and tremendous investment into training of another AI in another application area. So it's simply not affordable to do that. Another point, a large point, but nevertheless a very important one, is that large observational data repositories we can use for training of machine learning tools, they just represent the state of the medical art, but definitely not the need of machine learning. So on the one side, it is not clear whether artificial intelligence, our machine learning we apply on these data, just learns what the doctors are doing, or whether they are standing on the shoulders of the doctors. That is not fully clear. So it is not clear whether all the papers which are published on success stories of AI in medicine, whether they really learn what the doctors are doing, so not adding any progress to medicine. That is the one thread which is not clear today, how to tackle that. And another point is that a great challenge for AI applications in medicine is that missing data point. Missing data and observational data, which are just collected from the standard care in hospitals or even in doctors, in missing data is a part of the concept, because in each patient, a doctor diagnoses only that data he believes to be relevant for diagnosing a disease. But he will never do diagnosis and apply diagnosis for other diseases or for anything else. And this means that in patient data repositories, which are available today with hundreds, thousands and millions of patients, of course, these are, let's say, they have a structure like a Swiss cheese, because for all of these patients, most of the data are simply lacking. And that is indeed a point which is not trivial to handle for machine learning. So we must simply accept that in these observational data repositories, missing data is a part of the concept and not just an exception. So that is a threat indeed as well. Another point we have to take into account is that if we want to have huge data sets from observational data, then we have to pool data from multiple sources, so from multiple hospitals. But then a problem arises that, first of all, the populations in the hospitals may be different. So if we analyze, for example, patient populations in Aachen hospital in intensive care and in the famous MIMIC data, which is a hospital in Boston, with Israel Deaconess Hospital in Boston, then we see that some diseases which are very prominent in Boston, like suffering from shooting wounds and so on, so they are much more less prominent in Aachen. Vice versa, there are some diseases which are more prominent in Aachen and which are more rarely seen in Boston. So it is by far not clear whether the populations in the hospitals can be easily pooled without gaps in the multi-dimensional data space, which is hardly to explore then. Another point, which is by far less trivial, is that in the data, we always see the interaction between patient data and the doctor's action. We will come back to that because that is a primary concern, a primary challenge on medical data analytics, that all data represent the interaction of the doctor and the patient and not the patient only. So let's say, suppose now in a hospital B, they have a protocol, run a therapeutic protocol for a given set of diagnostic data, and in hospital A they run a different therapeutic set of protocols, and believe me, that happens. Yeah, then the data, if we plot that then and in a high dimensional data space, then the data distribution looks like that. And apparently, if we train our machine, an AI, on data from hospital B, we need exploratory features to predict hospital A or even a next hospital C, which may be somewhere in between. So that is a fundamental issue. And we have done some cross-coverage analysis of 4 intensive care station patients in hospitals, 3 within Germany and 1 within MIMIC in a US hospital. And we could show that the data in Germany do fit quite nicely within Germany, but the predictivity towards US is very poor, unfortunately. And that is an issue in practice because most AI is trained from US data simply because of availability. And if we transfer that then to Germany, we may run in trouble. And that is an issue which is currently not fully solved yet, as far as I know. Okay, let's now go a little bit more into the mathematical details. What can we do to tackle that? First of all, I would like to talk about extrapolation. What can we do about extrapolation? And one route to help here is to integrate knowledge and machine learning. That's what we talk about, hybrid modeling. There are various routes to do that, and all of them are explored in the context of medicine. Medical care, for example, the option is to use physics-inspired neural networks in order to integrate a priori known mechanisms like heartbeat models or signaling pathways and machine learning. That is maybe a route to do. Another route is to apply transfer learning systematically, so to integrate known features by pre-training. Let's say if you train on ICU data in US, you can do pre-training, and then you just have to apply transfer learning on the few available German data, etc. That has been done for image typologies. And and the markers for phase transition. So also this has been applied, so it works sometimes, but it is not clear whether it can be generalized to all the types of data which are currently available. That's an area of research and discussion. Another point I would like to discuss now a little bit more in detail, because that's one of the Aachen specialties. It's a so-called structured hybrid modeling. To be honest, it's one of my pet favorite areas of research. That is how integration of an a priori known structure of the process system of interest, and to integrate both such structures and known mechanisms. How can we? So it can be performed in the way that to integrate essential features by known operators into an overall machine learning, deep learning architecture that has been demonstrated by the Erlangen group around Andreas Meyer on medical image recognition, and they proved that such a strategy to utilize known operators representing known feature spaces really could reduce the demand on real-world training data and result in improved robustness of the machine learning model. Unfortunately, with such an approach, it is hard to achieve extrapolation features, and if we have a systematic bias in the features which are generated outside, then it may overrule bias-free real-world data. So the structured hybrid modeling approach by integration of knowledge and machine learning uses the fact that in case we have a system we want to analyze, to model and to simulate, which is characterized by multiple input variables, which are mapped to an output variable space. If we apply an unstructured data-driven model, then we have to tackle the full dimensionality of the input data space. So the idea between hybrid modeling is to utilize eventually known interaction structures of into a function of the system and to represent it into a functional network, such that each node represents a specific functionality within the system. And the edges represent the interaction between these functionalities, very simply, so that we arrive at a graph of nested functions. And the trick is now that some of these nodes may be represented by physics-inspired models, where if in case the input-output function is already known, or we can represent, in case this is not the case, we can substitute the nodes in I/O functionalities by black box functions, maybe represented by a neural network, etc., or others, ML machinery, and such that we arrive at a network of heterogeneous implementations of individual models, but each representing a small functionality driven by a small low-dimensional input space, and such that a structured hybrid model is characterized by a knowledge-driven interaction structure, and the nodes can represent either stationary or dynamic processes. Okay, the point now is that we can, the trick is now that we can prove that this integration of knowledge and machine learning can result in consequence, can as a consequence that we can reduce the dimensionality of the data structure which is required to train the model, to identify the model. So to characterize that, we introduce the so-called database, which is just a set of data, structured set of data, which allows to train the model, to identify the model uniquely. And in case the dimensionality of this database is 0, then the model is a mechanistic model, because then we have only to identify a finite number of parameters, and this can be identified by a finite set of isolated points in data space. So the database is conceptually zero-dimensional. In case the database is n-dimensional, namely the number of input dimensionality of the full input space, then the model is a black box model, because then we need to sample more or less tightly the range of interest in data space. And we can show now, and that's what we will see, that we can realize hybrid models where the dimensionality database is somewhere in between 0 and between n. So they are in the terms of modeling technologies, they are an interpolation between purely mechanistic and purely black box models. Okay, so here are some mathematical results showing that this concept works. One could show that the data demand for training a functional network, which has a tree structure, is controlled by the number of inputs, maximum number of inputs for any black box component in the functional network. And we can train these functional network models by from correlated data around a low-dimensional surface in the data dimensional data space. So currently, PhD thesis project is running in my institute to extend that to unstructured data distributions, and one can prove that such functional networks allow extrapolative simulations outside the covered data range, the covered database. And that is these are exactly the features we are looking for. So here one example, a theoretical example, which has been applied by my student Moin Samadi. We are currently now going to publish that, and it's in cooperation with the Institute of Martin Grohe. Sandra Kiefer is participating there. And here we showed that models which are characterized by such a tree structure, functional models with a tree structure, that these functional models with tree structure, that they allow us to train them, identify the model with a smaller subset of the data space, of the full data space, with a significantly higher performance than a neural network-based classifier. Neural network-based classifier, so showing that the explicit implementation of an a priori known structure really reveals and ends up in the superiority in training features and in extrapolation. Based on these results, we did a joint project with Bayer, funded by Bayer, together with Alexander Mitso's institute. And we developed an implementation of that structured hybrid architectures in a nested such that an architecture in TensorFlow, which allows to implement a nested mechanistic black box network and to train that in the TensorFlow environment. It is available now in an open source software package. And publication was published in the last day, so these are indeed very new results. And we applied that later on. I will show you one application results on the COVID prediction machineries. So this structured hybrid model concept fits pretty well to the medical needs, because in medicine, we typically have to find models which can be roughly structured into a three-layer modeling concept. First of all, for most of the diseases, we have a quite good mechanistic understanding for the molecular cellular mechanisms driving the innermost disease evolution processes. We call these core disease models. This is the primary focus of systems biology and systems medicine research of the last, let's say, 20, 30 years. So there is a lots of background in modeling on that side. Unfortunately, for applications in patients, we need to learn and to quantify all the impacts from lifestyle, environment, environmental conditions, genetics, etc. And here we are by far lacking explicit mechanistic knowledge. So we have to learn and to implement all these effects, covariate effects from outside by means of machine learning components, which have an explicit effect on the parameters of the core disease models. And last but not least, typically the state variables of core disease models can almost never be monitored in clinical settings. And simply because of of ethical reasons, to take biopsies every day, it's almost impossible. So we have to substitute the state variables of core disease models by machine learning driven models, which map the data we can assess in clinics and in home care, and to map that onto the core disease models in order to end up with an integrated model which realizes and represents an individual patient properly. Okay, such concepts can be realized here. I just want to sketch a very simple and quite older result, a study we performed on the adverse drug reactions of statins based on the so-called strength study, which has been performed here. Single nucleotide polymorphism, so the genetics of about 300 patients was assessed, plus some clinical parameters, and the goal was to predict the genetic constitution of patients which suffered from side effects of statins. And so we did that by separating physiological effects and genetic risk effects in such a very simply looking structure. We could then show by just analyzing the genetics of the statin action and the respective underlying metabolic mechanisms that we can go down to a substructures of nested genes. And so we ended up roughly with a functional network of integrated genetic interactions and physiological interactions. And learning this hybrid functional network structure, we ended up with a quite surprisingly good prognosis based on such a hybrid biomarker on the clinical phenotype with over 90% sensitivity and over 95% specificity compared, and this was a great success compared to genotype and black box based modeling only with standard complex biomarkers, which revealed about 70% of predictivity. So this was indeed, so we have indeed, in the meanwhile, there are some publications and some results showing that such implementation of a priori known structures, a priori known mechanisms into the model and complementing that with machine learning tools really can help to generate and to end up with much more robust and predictive models, which may help to fill our gaps in the data space. Okay, now I would like to end up with my talk with some, as promised, COVID data. So here, on the COVID data example, we can really nicely demonstrate the challenge of deconvolution of diagnostic data and therapeutic control. This is indeed a very universal challenge. On the example of epidemiology and predict and control COVID-19 dynamics, we have, from a mathematical point of view, we have to tackle exactly the same problem. Namely, we observe longitudinal data which represent state and age groups infections. So we have infection data and we have epidemiological actions, vaccination, non-pharmaceutical interventions, etc. What we do is we learn a model which maps the diagnostic data today and the actions which are set in place, and we predict then the future dynamics infection data. That's what we do currently, and that is a problem. in doing that, the epidemiological strategy, so the control mechanism set in place, vaccination, let's say, the willingness of people to get a vaccination depends on the situation, on the actual situation of the pandemics. So what we have to simulate and to model, and what we see in the data, is a closed loop control system. So we have the spreading of the virus represented by the system itself, which is controlled by some explicit control variables. We observe the dynamics driven by and in context of these control variables and the actions. And that is the problem, people learn these data, see these data themselves, and they begin to self-adapt to the system. And this self-adaptation, which controlling, let's say, spreading behavior or the contact behavior of people, this self-adaptation is fully unknown. We have simply no clue how this self-adaptation works in practice, and apparently this is one of the reasons why predictions of, let's say, spreading waves sometimes fail indeed. Okay, so that is what we have to tackle at the end. If we look at the data, then we have to simulate. Then we see that the data are indeed characterized by the famous spreading wave. So here we see first wave, second wave, then second wave, second peak, then the third wave driven by alpha mutant, then a small wave of end of holidays, then the delta mutant driven fourth wave we saw in November last year, and now we have the Omicron wave, which are currently going down a little bit. Each of these waves have been interfered with lockdowns, and some lockdown hard, lockdown light, Bundesnotbremse, etc. So you see there have been lots of actions set in place by government, but as well as self-adaptation of the population, restricting their behavior or changing the willingness to get vaccinations. And all of these together makes it very hard to predict whether a wave will really run into a critical state or not. So, but that is indeed the challenge we have to face, and there we are not really good. So where we are today, what are we going to do today? So what we have is here, that's a structure of the DV COVID-19 simulator as I developed for the application prediction of intensive care loads. So here the most boring part from a scientific point of view is the ICU module, because here it's based simply on statistics and some folding techniques based on data from Sentinel hospitals and the DV intensive data registry. So that is from a mathematical point quite simple. So here the scenario module predicting infection dynamics across the population, the age distributions in population is a much more interesting part, and there is a lot of science to be done in future. Today, most of these simulators for pandemic dynamics are based on so-called SEIR models, so they are essentially mean field models where the population is split into compartments, and these compartments interact with each other. And inside each compartment, it's assumed that the contacts and the infection spreading is quite individual quite homogeneous across the individuals, and the only heterogeneity and control of contacts, etc., can be implemented in terms of interaction between the various compartments. Very roughly, there are 4 compartments, namely some susceptible compartments which are healthy but can be infected, then the exposed infected which are not spreading, and the infected compartment, these are patients who are infected and can do spreading, and the recovered ones. So this interaction in these models is implemented by means of the well-known ODE systems. And So the nice thing is that these ODE systems can be established very simply. It takes just one day to write it down and to feed it to data, and everybody's happy. The problem now is that they are in fact not really predictive. One point is that the data which are used here and which are generated, they are quite rarely reported in the official data. So RKI reports just tell us as dot, roughly. That's what we see in the daily incidences reported, not more. We don't know more, and that is indeed for model fitting, that is indeed a challenge. Another point is that self-adaptation in these mean field models is a very, very new area of research. So the first publication which was published in that way was a publication recently by the group around Viola Briesemann and Kai Nagel. They implemented such a SEIR-based model, and they implemented some self-regulation, which were very roughly learned from correlates with some mobility data, etc. But it is very speculative. So these they could not. Also these predictions are, I would say, a little bit rough, and I would be very reluctant to apply that for prediction, let's say, of next winter's dynamics. So one point, if I'm skeptic, is very simply that I would claim that we don't understand the pandemic spreading. So we simply don't do that. One reason is that there have been early publications in COVID from May 2020 in PNAS from the group of Stefan Turner in Vienna. And then they showed on network-based modeling that the spreading of COVID does simply very often not follow mean field approximation, which is represented by SEIR models, ODE-based models. Reality simply does not fit to that. So they showed that if the contact the contact graphs the density of these contact graphs is below a critical limit, then the overall dynamics exhibits much more a linear dynamics and not an exponential dynamics, as is predicted by ODE-based models. So ODE-based models simply result in wrong predictions. We applied that analysis on German data here throughout the second wave, and in Germany we could, for example, show that in some areas of Germany we definitely could decompose the second wave dynamics into two components. One component which was driven by a mean field approach, and the second component around Christmas 2020 was definitely not associated with exponential growth. And so apparently we had a mixture. Dynamics of pandemic spreading is definitely more complex than people believe, and most models believe, and we have to take into account that, and there is no good solution. Anyway, what we observe in addition is that there are Germany-wide patterns indicating that the spreading of COVID-19 does not exhibit a full either chaos nor a homogeneous spreading across all age groups and federal states. So what we observe are very strange patterns, correlation patterns between these between the spreading, and we cannot interpret that. We don't know why this happens. These are just observations. So what we could do as well, what we did is to find out which are the driving factors of the COVID spreading is. We set up a hybrid model. This was a master thesis of Eunice Müller. Is a computer science student who is now working in the institute. And here we combined an LSTM approach, fed it with covariates across the states in Germany, and we implemented that in the hybrid HyperMod ML toolkit, and we implemented here into an SEIR model and combined that with an LSTM model, integrating the covariates, and he analyzed then impacts from various covariates across Germany, like age population, population with migration background, overall population in a state, and the density of population. And he saw that indeed this impacts the sensitivity of the dynamics of COVID-19 spreading was not homogeneous. So here you see that elderly patients, elderly persons were drivers throughout the second wave, but definitely not throughout the third wave. So apparently we have an inhomogeneous driving behavior between the spreading waves, and that is what we have to take into account as well, which is not really done with the today methods and tools which are available. I just want to jump over here. So we are now going to represent the dynamics by means of face portrait analysis. So we represent dynamics by means of geometric objects to make it more available for image recognition. And here what we could show is about the delta wave, that throughout Germany we see a very inhomogeneous, with the original data, very inhomogeneous behavior. But if we scale the dynamics, these phase portraits of the dynamics across the federal states, then we see a surprisingly homogeneous behavior across the delta wave across Germany, even in case the different federal states behaved very differently in responding to the delta wave. Most delta waves, most dynamics behaved very similar in terms of phase portrait behavior. And most surprisingly was our finding that the scaling factor we needed to map the overall, the original data onto these normalized data strongly correlated with the vaccination rates, indicating that all dynamics we observed in Germany was almost the same up to one parameter named, which is closely related to vaccination rates. So we are currently preparing a paper addressing that. So that is a surprising finding, because vaccination rate was definitely not a driving factor before. We could not associate migration data, for example, or age distribution data to be anyhow correlated with the scaling behavior. So apparently each of these waves shows some individuality, and we have to be aware of that, and we have to integrate that into a future tool, which allows us to analyze and to predict the overall control and the overall spreading of COVID, and that is what we are trying to do. So we are going to set up a hybrid model, a hybrid tool, which allows us to train the control behavior in terms of a hybrid approach. So integrating the learning, the interaction structure based on a simple mechanistic understanding, and to learn the interaction activities by means of parameterization depending on the explicit control parameters, and learned on the original data, as well as to learn the control mechanisms by decomposing political preference, societal preference, and societal adherence for vaccinations like vaccination or masks. So that is a research program we are currently starting in the context of a BMPF project Prognosis, which is going to start. Now it will be funded, and HDS LEE, that's a doctoral student, Joanna Meyer, which will do that. Okay, let's sum up. I hope that I could convince you that there is indeed a huge unmet need in clinics and public health for artificial intelligence. So it's a huge area where AI could change the world. Definitely, I'm fully convinced. But before we can realize the full potential of AI in medicine, we need to do some homework. So we need to definitely find methods and strategies to reduce the data demand significantly, to realize extrapolation features for AI, and to learn, last but not least, to learn patient-doctor interaction. That is a primary concern I have, that this must be solved before we can disseminate and roll out such tools in practice. So at the end, I would like to thank my co-workers in my institute. Here you see our COVID-19 outings where we can meet and without masks, and meet outside homework. And I would like to thank colleagues, especially colleagues in the BMBF Smith Consortium in the intensive care OEM here in Aachen, and my colleagues from DV, Christian Karagianidis and Stefan Weber-Kastens from Charité Berlin. And I would like to thank you for your patience. I know that I'm a little bit too long. Thanks for your patience, and I would be happy to take your questions.
Thanks a lot, Andreas. Let's give Andreas a big thanks. So I would like to open the floor for questions. So you can use the chat. I think the panelists can also start to ask direct questions. So perhaps I can start the first question, Andreas. So like in the beginning, you made a fairly, let's say, provocative statement that let's say many of the deep learning techniques do not work in healthcare, right? But doesn't that very much depend on the type of data? If you talk about, I don't know, random forest, etc., I think you're not talking about things like image recognition and these types of things. So could you elaborate a bit on like what general areas in healthcare it makes sense and in what areas not?
Yeah, absolutely. Thanks for that for your question. So you made absolutely the point. It was a little bit provocative because for the medical doctors, they believe that deep learning is the miraculous tool which can solve anything if you steer around in the data and you push the right button, and then the solution will come out. And that is what has been shown that this is indeed not true. As a data scientist, I directly believe. So apparently deep learning is superior, has a great performance in image recognition and these time series recognition. Also especially these monitoring tools for home care, etc., are impossible without deep learning. Their superiority is proven, and there's no doubt that this is indeed the method of choice. On the other side, there are lots especially in clinics or in clinical settings, or even in home care in settings in practitioners, the data structure is simply different. Yeah, so we don't have these long time series, neither we have image data. So very often image data are typically taken in radiology. So radiology is very much affected by deep learning techniques. So for them, it will be a game changer. So aside home care, but let's say even in intensive care where we have lots of standardized data, we have very heterogeneous data. No? So we have stationary data like gender or body mass index, etc., which does not change. We have on the other side ECG data. We have on the other side data of which are sampled twice an hour or once an hour or once a day or so. So data distribution is extremely heterogeneous, and has shown that for such heterogeneous data structures, deep learning simply in the status as it is today has its problems, and it's not superior. Also it works, but it is not superior to random forests. Some random forests sometimes outpace deep learning, sometimes not, so that is not clear.
Yeah. Sebastian has a question.
Yeah, thanks a lot for the talk. So I have a question about the structured hybrid modeling that you were presenting. In particular, I found this very interesting that you have this characterization about you measure the dimensionality of the database for the different types of models. From what I understood, so I have two questions there. Like one, like how exactly do you measure the dimension of the database? And second question is, can you also use that to basically anticipate how much data or what type of data you need for a certain type of hybrid model?
Okay, yes, the data, primarily the database, also this database concept was based on applications more in engineering science, in chemical engineering, where the concept was developed. So as it has its history primarily in chemical engineering. And in chemical engineering, we find data which exhibit a high degree of correlation, intrinsic correlation, because there are set points of processes, and there are data around these, the manifold of set points. The data exhibit a very high sampling density, and outside the sampling density is extremely poor. So that was a situation, and for such a situation, the first concepts of hybrid modeling have been developed, so the dimensionality is just characterized by, let's say, the nonlinear dimensionality of the manifold, which is tightly sampled. So that's a very rough, it's not a precise mathematical definition, I know. So for the mathematical proofs, I did with Bernhard Fiedler from Berlin, and there we assumed that the sampling rate on these manifolds is almost infinitely dense, more or less, and then you can prove that using such data you can identify the model up such that it can be extrapolated. So the problem now in medicine is that we have unstructured data which do not exhibit such correlates, and there it is much more tricky. That is primarily what we are currently doing in HDSL in a project by my student Moen Samadi, and he showed that it can be extended even to binary data structures as well, where we don't have such a correlate structure.
And when you know or estimate this dimensionality of the data, does that then also inform, let's say, the number of data points, the number of samples you would need to train a certain mechanistic model?
It informs that. And the other point is, if you know the data distribution you have available, you know the information you have to implement, because then you know that your black box, the input dimensionality, has an upper bound. So there have been implementations. So the first projects have been done with Wolfgang Marquardt more than 20 years ago. So that was work I did with Wolfgang Marquardt. And so there were implementations showing, you can show that it works. It follows the mathematics.
Yeah.
Okay, thank you.
Okay, so there are a couple of questions in the chat, and I will just read them. I'm not sure whether you can also see them, Andreas, but if I read out the first question, is how many treatments and or diagnostic methods are based on machine learning nowadays? How long will it take until the actual research will be implemented? What are possible obstacles? That's a very broad question, but perhaps you can make some statements about that. So does it play a practical role at this point in time? Perhaps is the question.
Today I would say the practical roles are not yet implemented. I think there are some tools. In US, I've heard that there was one machine approved by FDA, so that is available now for practical use in clinics. And FDA has set up a white paper how regulatory issues can be solved for AI. So that is, they have to learn that. To be honest, most applications are currently done in the context of pharma research. So to identify patient groups, do real world evidence, data analytics, etc., but not directly in clinics. So companies like Philips, Siemens, etc., they do huge investments into AI applications, especially in this monitoring and image recognition area. So radiology area so we can expect that there will be solutions available in the near future. I think it will not take too much time. In home care, I guess it will be very early because their regulatory issues are of less relevance. for maybe in the next few years, I guess, for clinical applications where doctors' decision-making is affected. There we have, we are struggling with regulatory issues, so it is not clear how regulatory issues can be solved, and we are currently working in such projects at the moment. So it will take a little bit more time, but I'm optimistic. Let's say in radiology, we will see solutions in the next few years.
Yeah, we are running a bit out of time, so I will not take all the questions. I just read one more question, and that is, can hybrid modeling be seen as an ensemble mechanism to combine different machine learning techniques?
One can see that way, yes.
Yeah.
Yeah. Also the key point is to implement explicitly the available knowledge. Also
yeah,
that is the key point.
So you did not talk about the details, like how it would exactly work, but are there certain, so you have a mixture of machine learning models and mechanistic models, yeah. But are there certain requirements? So for example, if you do backpropagation, yeah. Do you do it through all the different models, or is it decomposed in some way?
We can do it through all different models. Also, so if you have data available to train the individual models or some components, it is always preferable to do that. But it is possible to train the full functional network in a backpropagation step. Also that's what we have implemented in hybrid ML, also in our tool now.
But are there then requirements that certain derivative exists or something like that? That there must be some conditions then.
Yeah. Also we need derivatives. Also so the training is indeed an issue. Also training in hybrid models is, I guess, more sophisticated than it is in deep learning. Also definitely. Also there is no one-button solution. It can be quite tricky, especially if you have dynamic models implemented. So differential equations implemented as well. So this is then really tricky.
Yeah. Okay. I think we have to stop here. So thanks a lot, Andreas, for the talk. As always, we were running out of time. So okay. That was great. Marco just also kind of put some links in the chat. So we regularly have these types of colloquiums. So please follow the website, see when the next ones are. Do we know the exact date of the next one, Marco?
Yes, so the next colloquium will be on Thursday, 19th of May at 5 p.m. German time.
Okay. So just visit our website and you can see the details. So again, thanks a lot, Andreas, and see you all next time. Bye-bye.
Thank you for the invitation. Bye-bye.